Down.
M0 minus I.
Okay. So tell me the name. Don't tell me how to do it. What's the name say? What is phi of 0? It's an eigen vector for M naught. And the eigenvector? Which one? M naught is 5 by 5. They have 5 eigenvalues, right? Which one? Which eigenvalues? 1. This saying that M naught must have eigenvalue to 1 of them. I don't care what the other one is. If it doesn't have eigenvalue to 1, you cannot have any solution. And that's the case for R. Right? If you look at R, R is the case when you have eigenvalue to 1. It's a simple one, right? If it's 1, so 1 equal to 1 times 1. But arbitrarily, okay, if you put on 4/3, 2/3, and 4, 4/3 in here, it will not have eigenvalue to 1. The third converge. And you can actually show that with eigenvalue to 1, meaning that you have 1 0 pi on the filter H naught. They all related. Okay? Okay? So the sufficient condition for all this to start is that you have to have an eigenvalue to 1 for M naught. Okay? And then, if this is the case, then you can start, right? And phi naught is the eigenvector associated with its eigenvalue. Once you can do that, then you can start everything. Because this is dependent on phi naught. But this is M1 times phi naught. Okay? So this is a very strong condition on the filters. And you can show that this condition is the same as the filter H naught of Z has 1, 0, and pi. It's a theorem in the book. I showed it. Okay? So let me have a discrete point. How many points do I want to compute? Right? If you have, I want a very fine resolution and so on and so forth. I might want, 2 to the 5th or 2 to the 10th. Right? Iteration. I have very fine representation of my basis function. But if I don't care, if I only want 2 to the 3rd, I can stop at at the 8th iteration. Right? So this particular process here using recursion is a way for us to very efficiently implement or compute the basis function. Right? You can how many points that you need. You can basically compute, right? And the algorithm here is that if you look at 7, 8, if we see the binary representation is 1, 1, 1. It's basically M1 times M1 of phi naught. Okay? So that's easy, right? For the case of R, you can find this easily. So if I want to use the same process here for a longer length system, right? In this case, all 5. I have to somehow, write a correspondence form. Okay? As in phi naught times M naught, phi naught, T1 half, and so on and so forth, right? And the way to do this is using a vector matrix representation. And you can show that given H, I can always find this matrix M naught, M1. And if this is the case, I can basically use the binary representation, right, to compute any point. Provided that I know where to start. Right? So what is the condition so that I can start this process? The condition is that phi naught has to exist. Right? And looking at this equation here, P naught is an eigenvector with eigenvariable 1. And you can show that this is the same as having the filter having 1, 0 time. Okay. So we find the condition on the matrix M naught and or the filter H naught such that there's solution for those discrete points. But the solution might not be smooth, right? I can start. It might be, that. Okay? There's no guarantee that this gives you a smooth solution. It could be like this. Okay? Compare this particular solution with this one. What's the difference? What's the difference between a smooth solution and this solution? Frequency or derivative, right? Things like this. You might not have any derivative for those points. And this you can find derivative. Okay? So what I'm going to do next is I want to say what additional condition on H naught such that the derivative exists. Right? So what if I take the derivative of phi with respect to t? And see what's the corresponding equation. And I do the same thing. And hopefully I can find a corresponding condition on either M or H such that this derivative exists. I can go for phi or 2 and so on. Okay? The more derivative exists at those points, the smoother the basis function. Right? Because let's look at the first derivative and see whether you can make any deduction for the condition on M naught or H naught. Okay? So I need to tell what is the derivative of phi with respect to t. 4 phi of t prime whole thing here is 2 become 4. Exactly the same form. So if I were to do exactly the same thing using phi primes instead of phi. Okay. So I have phi prime of 0, phi prime of 1, phi prime of 2, and so on and so forth. Would this change? This will be phi prime. Right? Would this change? No. What changed? This 2, right? Become 4. So what would be the vector phi prime of 0? I'm looking for something like this. Okay? What would it be? 2 M0. So what is the condition on M0 now? So that the derivative exists at those points. 1/2 eigenvalue, right? This means that if I put 2 over here, I have a 1/2. Look, it looks like a eigenvector equation, right? So we have M0 and phi prime 0 is 1/2. So it means that M0 as an eigenvector is equal to 1/2. And you can show that it's not 2, 0. Hi. You're forcing one eigenvalue to 1.